Okay, thank you very much, first of all, to the organizer for giving us the opportunity to talk about our projects. It's also great to actually have Jerome Feist before me, because it's actually a project that we collaborate. I'll come back to this in a minute. So OpenSense, multiple institutions involved, is really focusing on high resolution air quality sensing. In this case, not only in Zurich, but in Lausanne as well. So why we do care about air pollution at all? So there are evidence that there are major impact on the human health, thanks to actually various pollutants. There are various studies that confirm this, and the problem is not getting better. It's actually getting worse because the population in urban settings is increasing. What makes the problem difficult is simply because air pollution is very, I would say, time dependent and space dependent. So you have essentially traffic patterns, temporal pattern coming from weather, and maybe specific peculiar industrial installation that might actually influence your particular urban settings. What we do today, there was a question before about how clean is there in Zurich. Well, we have NPA specialists as well on board. And actually, the way that these things are measured and assessed these days is with, would say, 1 or 2 stations per city. Actually, the whole Swiss network of these monitoring stations are high-end, very precise, is 16 sites of the whole country. And typically, these measurements are then interpolated with what they call the mesoscale models with about, I would say, 1 kilometer square cell. So that's state of the art today. Our vision as a project is actually, we like really to essentially go behind this envelope, obviously, by bringing in additional sensing sites, exploiting public transportations, and actually endowing public vehicles with dedicated instrumentation, diffusing also to private citizens portable devices that can measure, that can contribute in this kind of dense spatial measurement network, if you want. And obviously, we'll not forget all what information is available from land use, population density, meteorology, and so on, that is measured regularly on daily basis. The goal, as I said, is really kind of achieving a high resolution pollution map, and we'll see what we can do at the end of the project, but we're really going beyond this 1 kilometer square that I just mentioned. We're not happy only to do this. We like to really kind of to close the loop and getting essentially this map used by either officials or private citizens if they have to assess a little bit their exposure, but also the very same private citizen that actually can carry around these kind of, I would say, handheld sensors on their bike and houses and so on. So this is a little bit the vision of the project. So in order to achieve this vision, we have a multiple, I would say, piece of the puzzle. And this piece of the puzzle, this is the backbone of the project. We're already existing in OpenSense 1. So there are 3 big pieces, if you want. One is obviously the mobile, or I would say the sensor deployment. In this case, we exploit mobility. The second big piece, very important for us, also distinguishes our project from other parallel project in Europe and worldwide, is data quality. And finally, producing maps that can be used by official or citizens. OpenSense 2, what it did is essentially adding this kind of crowd sensing platforms, if you want, techniques. And finally, we brought in the SHUV, the hospital here, and the IST, institute that cares about work health, for actually having already a small, I would say, health case study that can somehow take advantage of these increased density maps that we produce. So we'll start with the deployments. These are things that have been going on already in OpenSense. We keep improving, keep maintaining. It's non-trivial. We have 10 buses in Lausanne and 10 trams in Zurich equipped, and we have various small static station that we add. We have also dedicated vehicle. You will see in a minute how do we exploit this. Maybe the highlight is what already Jerome mentioned. Here's the same slides. Actually, we have one co-PI, Lukas Emenegger from EMPA, that is in both projects. And I think this is a very nice, I would say, collaboration, inter-project collaboration, but also that stimulates somehow intra-project collaboration between, in this case, TIC at the ETHZ and EMPA. So they had to actually get together for getting this instrument on the tram. Another very interesting contribution, I think, is that here we're talking about big data, about millions of sampling gathered every year, essentially, and we have to manage somehow this kind of data, big data, in the back end. And here we have the group of Karl Aberer here at DPFL that actually created this back-end middleware called GSN, Global Sensor Network, but also what is nice is that then this GSN is also propagated to Zurich, and we have essentially the same interface for someone outside that want to access the data is actually talking to the GSN middleware. And I'm happy to report that essentially also Lausanne was a little bit behind in terms of deployments, but since several months, our data are publicly available. Most of them are uncalibrated, but I mean, the GSN is working in a stable platform on both sides. If we now talk about crowd sensing, which is the novel aspect in this project, so we started already at the end of OpenSense 1 to actually do our in-house prototypes, see what we can attach to smartphones. We tested various available platforms, the variable node here, the air quality HAG here, and compared, we have the chance to have EMPA in, among the various partners in the consortium, and always comparing for data quality with their high-end stations. And unfortunately, we could not find, I mean, these devices were working properly on all sort of, I would say, computation and communication, but in terms of data quality produced, they were not sufficient. Either they were lacking of the necessary sensitivity, or they were not properly calibrated. It was difficult for us to actually hook in and properly do calibration. So thanks to Nanotera, once again, there was a call for strategic initiative. We applied, and we actually got a project that had a poster and demo here, still available if you want, called OpenSwiss, which essentially allow us to design from scratch, possibly with industrial partners. We're still in discussion with various SMEs, a platform for crowd sensing, and we will be able to also leverage, I would say, a lightweight version of GSN. It's called Tiny GSN, for essentially managing the whole network of these sensors and incorporating in the global network that has also trams and buses information. So this is a collaboration between my lab and the lab of Karl Aberer, and we report regularly to the consortium of OpenSense in order to get the ins and hopefully have advanced user down the road when the device will be ready. So in the meantime, the group of Karl is already working with Tiny GSN on these devices, looking into various algorithms for location privacy protection and integrating in the whole network, as I said. So now, if we go to data quality, which is very important for us, I think there have been various work, but a very, very nice work by the lab of Lothar Thiele in Zurich. This is last year resulted in a paper award where they actually came up with algorithms that maintain the error, calibration error low over multiple hops. Essentially what you want to do, these noisy sensors are low cost, they drift over time, and you want to essentially exploit all possible calibration opportunity that you have with meeting reference stations or from bus to bus and so on. And so this is actually really, so that's the performance of the algorithms in comparison to a standard least square algorithms that you see in red. They actually took another direction this year, very complementary, and the overall goal is put the two together, where essentially they bring an array with of sensors with selected sensors. So these sensors are not only, I would say, drifting and noisy, they are also cross-sensitive. And the overall idea here is actually to calibrate the array of sensors that might contain also temperature and humidity sensor in order to get better results. So that the next step will be to put the two calibration techniques together. And also in this case, we have a demo and poster here on the annual meeting. On our side, essentially, we have been looking into another aspect of these low-cost sensors. So these low-cost sensors have also slow dynamics, and essentially you are mounting them, in this case, on very fast vehicles. So we have a setup here. We have a wind tunnel. We can kind of process very precise experiments with, thanks to a Cartesian robot inside the wind tunnel, and reference instrument, in this case is a PID instrument, very fast, in order to actually really understand what is the impact of this dynamic. And so here, as an example, you see a CO sensors, and you see the ground truth in black, and you see essentially the signal that you measure here in red without any processing. And in order to compensate that and really carve out essentially making sure that this picture that you have of the field is not blurred, you can have two different techniques. One technique is actually deconvolving the signal, knowing essentially a good estimate of the model of the sensor, and another technique is actually using active sneaking. So pumps, fans, and actually also doing some computational fluid dynamic analysis so that you can fine-tune where you sense where's the inlet of your sensors. And here you see an example how we exploit the C0. We mounted side by side the two sensors, one with a passive sampler, the other one with an active sampler, and carefully designed inlet. And this is a drive of 1 hour where you see essentially the signal-to-noise ratio that is increased by a factor 3 or 4 on this sensor. So with very simple, I would say, flow pre-processing. And also in this case, we have a demo and a poster. If we talk about crowd sensing, this is even more important. I mean, this sensor crowd sources, so to speak, can be even more noisy. They might be mismanipulated. There might be essentially malicious attacks and so on. And here we have a nice contribution by Boy Folting's group on reputation systems that over time essentially try to maintain essentially the error of the contribution low, and they simulated various attacks to this network in order to actually being able to discriminate from good contribution from malicious contributions. Another aspect of this crowd sensing on the algorithmic aspect is how you select these sensors. You have a lot of them, but not all of them contribute with the same quality. We like to actually essentially, through the sampling, separate from sensors that contribute to the whole picture in a good way, and sensors that in sense are noisy and maybe very heterogeneous, and so they don't contribute to this. So they came up with another adaptive sampling algorithm that can be proved with tight bounds in terms of sampling complexity and guarantees in order to actually go sampling the right number of sensors in order to improve the overall picture. So now we're talking about mapping, and it is very important also to have mapping methods, because I'm sure if someone wants to use this data, okay, you sample in various lines of the buses, you maybe have your kind of crowd sensing platform distributed, but I'm sure someone else will find a place where you need to an estimate of your pollution field and you didn't sense there. So how you interpolate, how you go behind essentially the coverage of the network. Here, EMPA, they are specialists on this. They actually did a very nice job. They essentially came up with state-of-the-art Gram-Gral framework where you try to really kind of leverage all what you can in order to do this job. So you start with essentially creating a precise wind field map. Then you go down to the building level by using computational fluid dynamics method, and then eventually use a Lagrangian dispersion model to produce the pollution map very precisely. So this is quite remarkable results. If you look the numbers here, we're talking about state-of-the-art 1 kilometer square. They are down to 5 meters grid resolutions. They have hourly output. They can kind of predict a little bit the concentration on a band up to 30 meters from ground level. And very important, they can go back and forth in time. As long as you have meteorological data and these emission catalogs that the city keep track, you can go back and forth in time. And maybe you have health data that were collected at a different time period, and you can correlate thanks to these techniques. And what is more amazing is that here you see a comparison of the simulation created with their framework and the observation, the single point measurement of the Nabel station run by them. You see how good it is. And remarkably, there is no data that has been used for producing the simulation, only the data of the meteorological stations and the catalog of emissions. So there is no pollution data introduced in the model to get to this level. So this is very good. Another techniques that we have been, we reported last year, but I wanted just to mention here because we keep going. We don't have a poster or a demo on this. It's essentially a completely different techniques based on probabilistic modeling, where you try to, again, exploit land use data, but also push as much as you can the relation, the probabilistic relation between your measurement data for going behind the coverage of the network of the buses in this case. And we have various algorithms and also provided very good results. So finally, the final block is on health data. This has been going on since a while. The collection of health data, and the colleagues of SHUV and IST always have correlated with what they had, which is this single measurement point in the middle of Lausanne. And thanks to our project, now they can really kind of compare this data with maps that we produce in the project. So there are some preliminary results here. The first correlation is that between PM10, particular matter 10 micrometers, and these OpenSense maps. So you see here in the kind of violet band what they could do before, and here you see what they can correlate now in this white band between the various inflammatory markers and the data coming from OpenSense. So they confirm the trends and so on, and they have way more details because we can play with this temporal and spatial resolution that they could not play before. And maybe also interesting for some of you, we mentioned already last year, but there is a pilot study going on. It's a classical way that they do at IST and SHUV their studies. There are 24 participants. They come to the SHUV, they equip with backpacks with all sorts of instruments, and then they track and they have to participate to the study. And the good news here is that we are almost done with this study, so we have almost 80% of the data gathered, and in a few months we'll close the loop here. So if I come to the conclusion, I hope that I gave you an idea that OpenSense is really caring about this kind of multiple platforms with various, I would say, accuracy and advantages and drawbacks, from static high-end monitoring station to crowd sensing platforms. I also hope that you get the feeling that we develop technology and methods somehow for end-to-end system. We create a whole pipe, and all these different elements, these different pieces of the puzzle are relevant for OpenSense, including the recommendation to public citizens through maybe their smartphone. Data quality is critical. I try to give you a little bit a snapshot of how important it is and how important it is for us also for distinguishing our project from other concurrent projects in Europe and worldwide. And thanks to Nanoterra initiative, we got this strategic initiative that allow us now to really kind of move forward on this crowd sensing platform that has been for a while a major bottleneck. And maybe my personal take on a challenge at the end, now we are in an extremely good position to maybe have a grand challenge scientifically, really kind of see how to compare this kind of data-driven, dense measurement techniques, extended maybe probabilistic models, with more classical dispersion techniques like the one that EMPA used. So how do they compare? Can we kind of leverage one for the other, and so on and so on? I think we are in this unique position where we can do this within the consortium. And by that, I wanted to conclude, and thanks everybody in the project for a great help. Thank you.
Okay, we have time for a quick question. No questions? You have one. Good.
Can you say that the cheap sensors you can get on the market for the crowd sensing can be made reliable with the calibration and signal processing?
Partially is true, partially is not. In the sense, the key point is that, and that's what guided our design, you have to make sure that essentially the sensitivity of the sensor is at the level of what you want to measure. If the sensor, and that is actually one of the key points why the platforms that we find on the market don't work, because essentially when you use in the, I would say, in the targeted space that you want, that they measure only noise because they're not sensitive enough. This is one point. All the rest is not fantastic, I would say. You have to spend, as you saw, a number of effort for compensating the slow dynamics, compensating the noise, and so on. But there are solutions, so to speak. And I think when we started this project, people didn't believe that we could get this type of results. Now, essentially, thanks to various expertise and eventually ground truth data provided by EMPA stations, we can show that essentially we can get to this point. That's my take. I think we are really at the beginning of really exploring, particularly for mobility compensation. I mean, we just explored a few things. So you look in the literature, there are very little publication and data reported on this. These are sensors done for static application, I would say, not mobile on trams.
Okay, let's thank the speaker again.
Thank you.